Hello! This video presents a demo for the blockchain-based federated learning environment and data marketplace by Fondazione Bruno Kessler and IBM. We're going to assume that you're familiar with blockchain technology and its basic concepts. What is federated learning? Federated learning is an emerging approach to establish cooperation between a group of agents that are solving a machine learning task. The goal is to improve each agent's performance without disclosing any data. This means that one organization has to trust another organization to locally execute the machine learning algorithm on its premises using its own data. Since the computation is defined by one party, the algorithm's owner, and the data is owned by another party that also runs the computation, there may be an inherent trust problem. How can we ensure the correct computation is performed and that the reported results are the corresponding outcome of that computation? What do we want to achieve? We propose a framework that allows the computation to be delegated to the data owner while ensuring the provenance of the computation process. This framework supports the sharing and trading of the computation results in a controllable and secure manner. What's the scope of the work? This work is a joint collaboration between FBK and IBM as part of the INFINITECH project. FBK developed a fraud detection federated learning algorithm that's run by a consortium of organizations on their own nodes and on their own data. But these organizations all share the intermediate learning results with each other to achieve higher precision. IBM provides a blockchain-based secure execution framework for the distributed fraud algorithm execution, recording all the meta information about the algorithm's execution and recording the shared intermediate results on a transparent, immutable, and verifiable ledger. At the end of the execution, a completed model can be shared as a tradable asset on a blockchain-based data marketplace, which is also developed by IBM. The blockchain-based data marketplace provides a tradable assets catalog where consumer organizations can search for and access available assets by paying for those assets using digital tokens. In this demo, you'll see the entire flow. It starts with development of the federated learning algorithm and publication of the algorithm image. Next, the image is run by multiple organizations who share the intermediate results on the chain. After that, we show creation of the completed model and how it's published on the marketplace. Finally, you'll see how this model is then purchased by an external organization. But first, here's some background on the demonstration environment. For the demo, we have a Dockerized deployment of the Fabric blockchain on a Linux machine, along with an API service client application implemented in Node.js. This client application wraps the Fabric JavaScript SDK and provides RESTful API services for interaction with the chain codes that are deployed on the blockchain network. We have a local Docker image registry for storing the algorithm image, but of course any other image registry can be used to publish images. During the demonstration, Docker containers from the federated learning algorithm image are instantiated and run locally, but they can also be run in a totally distributed manner as Kubernetes pods, for example. Here are the steps of the demo scenario. 1. First, the algorithm developer builds a Docker image for the federated learning algorithm. 2. The developer publishes the image to a Docker image repository. 3. Then he registers the image metadata on a chain by interacting with the blockchain platform through the API services client. In the next stage, the consortium of organizations that runs this federated learning algorithm starts the distributed learning process. 4. The admin runs the script to initialize the learning process, and the image metadata record is read from the ledger. 5. The Docker image that is based on the image metadata is pulled from the image repository. 6. The distributed learning process is initialized by pulling the appropriate configuration information of the participating organizations and their respective computation nodes and creating the learning process record on the chain. 7. Next, the learning process orchestrator script needs to run the first iteration of the computation on all the nodes. It creates an execution record for each computation on the chain. It also creates private and public keys for each computation task and stores the public key in the execution record on the chain. In the following step, the private key will be passed to the Docker execution container where it will be used at the end of the computation to sign the results. 8. In this next step, the orchestrator script creates a Docker container from the federated learning image for each node running the computation. It passes the private key as initialization to this container, and this container is executed on the organizational node using the organization's data as input. At the end of this execution step, the results of the computation, signed with the container's private key, will be used to update the execution record created for this container. The chain code that writes the result on the ledger checks that the signed result matches the public key stored in the execution record. In this way, it makes sure that the result is indeed reported by the correct execution entity. Steps 7, 8, and 9 are repeated in a loop until each node finishes its calculation. At each iteration, an execution record is created per node, and containerized execution of the image is started on the node to pull organizational data. The previous results by other nodes are pulled from the blockchain execution records for previous iterations. The computation is executed, and the completed signed result is published on the chain. At the end of the computation of all the nodes, the learning process status is updated to completed. The final outcome of the computation is a completed model that can be traded with external organizations. This model is stored on the blockchain data marketplace. The tradable asset record on the chain contains metadata related to the asset creation process. For the federated learning model, this information would be, for example, an algorithm image that was used to create the model, the learning process that produced the model, the owner organizations, and the price. This information is searchable and can be used by organizations to search for and find interesting assets for consumption. The record of the asset also contains the model binary itself, which can be traded with external organizations. The red arrow represents the actions of an external organization that is working with the data marketplace. It can search for appropriate assets by querying the blockchain data marketplace. It can then request access to the selected assets. If the organization has enough funds in its token account, the access request will be created and approved. Otherwise, it will not happen. When an organization tries to access the asset, the chain code checks that the access request for this organization was approved and that this asset exists. The access is either granted or denied accordingly. To sum up, we presented a blockchain-based secure execution environment and data marketplace for fraud detection federated learning. The possible extensions to our work include the following. We can use the same framework to support the execution of various algorithms, as long as they can be represented and packaged as a computational task in a Docker image. In the demo, we demonstrated cross-chain code invocation of previously developed ERC20-based token smart contracts inside the data marketplace. Instead of ERC20, any other ERC-based token smart contract can be used in the same manner. In our demo, we also showed simple functionalities of a marketplace to illustrate the digital trading of learning models while applying tokenization on the blockchain. This data marketplace could be extended to provide more functionalities, from richer query capabilities to pluggable pricing models and advanced trading options such as auctions and price negotiations. Thank you for listening.